So yeah, first of all, I'm very sorry for being late. It's 99% my own fault. And I'm also very sorry that I'll have to leave early as well, but that's mostly Cambi's José's fault. So not everything is my fault. And if you don't like the results, that's actually Matthias' fault, because I should say that I didn't know he was also joining before I said I was going to give this talk, because I think it was the most relevant to this school. But I should say that Matthias did a lot of the heavy lifting for this work. Yeah, I should actually thank the organizers for giving me the opportunity to speak here again. And again, sorry for being late and keeping you here. Anyways, let's get down to business. So yeah, so in this work, we're gonna talk about generalization bounds for quantum machine learning. And let me first set the stage and keep things classical for a while. And then I'll be, so that we can explain what we're actually doing. So we're going to assume you have some data set S, and you're given some labels. For now, let's assume maybe that you're just like 0 or 1, and that they're IID. And you want to output some hypothesis. I'm going to just keep things very abstract for now. But importantly, we're going to see this sort of learning procedure as a channel. So for now, everything is classical, so really a classical channel that takes these samples and outputs some hypothesis. And in this way, you can really see sort of this whole learning procedure as just something that takes your samples and then outputs the hypothesis. And this joint distribution is then sort of a channel, like when you transmit information. Now, once you've then trained your data in some way, I'm not really specifying how you're getting your hypothesis, it can just be any way. You then want to test whether you're actually doing something reasonable or not. So one way you can do this is just get some new data from the same distribution, and you can then output some labels, say, given the hypothesis that you've obtained previously. And you want to know whether, given a good performance on the data you trained, you also get some good performance on data you haven't seen yet. So this is sort of the setup of the bounds we're going to talk about. And so how can we formalize this? Well, you could think, for instance, that given your data, you want to form a hypothesis by optimizing some sort of loss function. So this function L here is just something that you're gonna try to find some W in your hypothesis space that minimizes this loss function, which in some sense captures the mistake you're making by assuming this hypothesis W. And you just want to make sure that the expectation value of this thing is as small as possible, so that your mistakes are kind of small. Now, we don't really know the measure from which we're sampling, so we cannot actually just compute this minimum. We just have access to some samples, and well, what can we then do? We can just minimize the so-called empirical risk, right? Which is just the loss function evaluated on the samples we've got before, and then we just take the average, and you could minimize this thing. Now, but in principle, right, there could be some sort of discrepancy between minimizing the empirical risk and minimizing the true risk, right? And just to give you an example, let's say we want to find some sort of a polynomial that interpolates well some noisy points, right? I could just pick the degree of the polynomial to be the same as the number of points I have, and then I'm gonna interpolate perfectly and reach every point. But this is gonna give me a crazy wild polynomial, so if I actually add some new points, they could be very far away because I did some overfitting. So it's not really the case that you wanna always make sure that like you fit perfectly to the data you have, right? And what you actually want are procedures that have a small so-called generalization error, which compares like how well sort of you're doing on the samples you're given versus like the true error in the sense, or like over the whole distribution. And this difference here is what we call this generalization error. Now, and again, if you're controlling this thing, you're making sure that you're not overfitting. So if you're showing that this generalization error is also going down and converging to zero, you're in some sense showing that you're not overfitting to the data you were given when training this algorithm. Okay. So, any questions so far? Nope. Okay, then now there are in the classical world quite a few results on how to bound these things and their various setups. But I'm gonna present to you one we liked a lot, which has this sort of information-theoretic flavor. And before that, let me just introduce you the relevant quantities. Classically again, we're gonna get quantum in a few minutes. And the first thing you need to look at is the so-called classical mutual information. So if you know the Shannon entropy, the mutual information between X and Y is just the entropy of X plus the entropy of Y minus their joint entropy. And what I find a bit more intuitive is to actually look at the mutual information in terms of the Kullback-Leibler divergence, the relative entropy between the joint distribution of X and Y and their marginals. So if you think of the relative entropy as some sort of distance, it isn't really a distance, but it's instructive to think like that, then this is just measuring how far, in some sense, your distribution is from being true independent, how far your random variables are from being independent. And operationally, it tells you, so you can write it as this expectation value over here, and it tells you how much you learned somehow about X after you've seen Y and vice versa in terms of, yeah. Okay, now what is important is that, as is clear from this formula over here, is that this thing is zero if and only if your X and Y are independent. And it satisfies some very nice properties like the chain rule, data processing, and so on. So this is a kind of well-behaved quantity. And you can also consider the quantum mutual information, which is what you get if you replace the Shannon entropy by the von Neumann entropy, or the same way the usual Leibler versions by the quantum relative entropy. And the properties are sort of the same. You have that this thing is non-zero if and only if the states are in a product. Now, another thing I'm going to have to tell you for a second is that is to consider the sort of concentration properties of random variables. This is another ingredient necessary to present our result. And to do that, we will consider sub-Gaussian random variables. In our paper, we actually consider just general sort of bounds on the moment generating function of your random variable or quantum state, but here let's stick to sub-Gaussian. So we say that a centered random variable is sub-Gaussian, sigma sub-Gaussian, if you have this sort of bound, right, for the moment generating function. And it's the same as saying that you have some sort of Gaussian concentration bound for the tail. And well, what are good examples? Of course, Gaussians are sub-Gaussian, very surprising. But generally speaking, you can take, for instance, just any bounded random variable. You then also get sub-Gaussianity or bounded observables and so on. And what is nice is that if you look at, for instance, averages, then you have some sort of decay in this sub-Gaussianity constant. So if you take, so in some sense, if your random variable is well behaved enough, then you'll have something like this. But not, of course, every random variable satisfies this. So we also consider less stringent bounds in our paper. But I'm not going to discuss those cases here. Okay. Now, I'm finally ready to present sort of the classical result that inspired us. And it's this result by Xu and Raginsky from 2017. So it tells you that if your loss function is sub-Gaussian, and then the generalization error is bounded by the mutual information between the hypothesis and the training set. And you have the following bound here. And n is the number of samples you've took. So why is this interesting? First of all, this led to many different works. But this tells us somehow, so this generalization error, so the sub-Gaussianity assumption over here is telling us that in some sense, like where you're gonna land, depending on the data, is a random variable that is not like behaved in a very crazy way, that you have some sort of concentration inequality. Right? So this is what the sub-Gaussianity assumption is saying. And this mutual information bound here is saying that somehow, if I know what the value of the hypothesis is that I spit out, I cannot reconstruct what the data was exactly. So I'm not revealing too much about the data I've used by taking the hypothesis. The dependency isn't too big. But note also that you also don't want this thing to be too small, right? Because one very easy tactic to have a good generalization error, as you can see from this bound, is just, for instance, to make the hypothesis completely independent of the data. Then you get a zero. Yeah, sorry. Yeah. So this is just a value you're given, right? Like a label. So for instance, for it could be just like, so if let me maybe go back to the definitions, and then it might be easier to see. Oh, a lot of clicking. Yeah. Okay, so we're just given some labels, right? And then our goal is to sort of, the loss function then depends on those labels and the hypothesis. Does it make sense now? All right, so the point I was trying to make now is that note that this is telling us that we want the mutual information between the data you've seen and the hypothesis to not be too big, because this way we'll get a good generalization error. But of course, we also don't want it to be too small, in the sense that in the extreme case where this thing is zero, then the hypothesis is completely independent of the data. which means that, okay, you have great generalization, but your algorithm is outputting a terrible hypothesis probably. Yeah. You have another question? Yeah. Mm-hmm. Yes. Yeah, so you should think of it this way, right? So maybe try to think of it from a communication point of view, right? So you have this training set, and then you sort of it goes through this channel, and at the other end you get your hypothesis, right? And your algorithm is this channel, this noisy channel in some sense, right? If what I'm saying is that if you want to have good generalization, at least according to this bound, while you're doing this, like this process that gets you sort of the training and then the hypothesis, to lose something along the way. Because if you don't lose something, if you lose something along the way, this mutual information will not be very big, right? Which will tell you that you generalize well. And this sort of intuitively speaking means that whatever is coming out at the other end didn't depend on a like is not completely determined by the training set, which means that sorry, the other way around. The training set is not completely determined by this hypothesis, which means that you're not overfitting probably. Yes. No, I think you. Yeah. Please go ahead. No, I'll take his question later. Mm-hmm. Oh yeah. Sure. Mm-hmm. Yeah, so that's a very good point. Of course, I'm not saying that. I think this sentence is probably misleading. I'm sorry about that. So this one. I'm not saying that that sort of you can evaluate this thing explicitly, but first, like I like it from a conceptual point of view because it tells you sort of conditions under which you have generalization. But for some procedures, so for instance, later we'll talk about the case where you assume that your learning procedure has differential privacy or other things. Sort of, if you can show that the different steps of your algorithm are making you lose some information along the way, for instance, regardless of what the input was, then you can control this mutual information. So there and this I think was one of the hardest parts of actually getting the quantum thing, not the quantum thing to work, but to get applications, is precisely that you sort of need to find setups where you're able to get a non-trivial bound on this mutual information because of the way you're doing somehow your estimation. Does that answer your question? Yeah. So, for instance, one way you can a handle on this is if you have a so-called strong data processing inequality. So if you can show that the channel that you're implementing does not only sort of reduce the if you have a stronger version of that you're losing information at a certain rate, for instance, then you can control this better. Yeah. Also had a question? Mm-hmm. Yeah. Yes. Mm-hmm. Mm-hmm. Yeah. Other questions on this shoe setup and why we like it? Nope. Okay, then let's go. Um, so first, I should say that part of this work was also trying to just start of thinking, how do you define these quantities if you have some quantum learning procedure, lots of things you can quantize, how do we do it? Yeah. And another thing, and once we have formulated the relevant quantities, you of can we get a quantum version of this Raginsky result I showed? Oh, I should also you actually prove it. So it's not too hard actually. You just you use you combine some variational expressions for the relative entropy with your sub-Gaussianity assumptions, and it's I should have maybe even presented it. It's the classical one is quite easy. It's by Laginsky online, which are very nice. I highly recommend looking at them. Maybe I can send them to you later. Okay, so I'm gonna now go to the quantum part of the talk and sort of explain a bit how we model the classical quantum learners, state our generalization bounds, and some applications. What question like how do you actually work with this? So what we're going to assume is that what we are actually given, so sort of this data before, we were just is some classical quantum states. Okay, so what are we modeling here? So S is your label, and you're going to assume it's classical, and rho of S is then the corresponding quantum state to that label. And we are also then samples, and we're gonna assume that we have this tensor product structure. And I once again want to see sort of learning procedure as a quantum channel. Okay, so sorry, as a channel. So the natural generalization is, of course, then to just consider a quantum channel a CPTP map. Now, the learner then will perform some POVMs on the training states, which will then sort of have some outputs related to hypotheses, and this will then be mapped to a hypothesis state. Okay, so this is so in this way, what is going on, and this might be a bit complicated to see, but essentially what you get in the end by thinking of this procedure is a quantum classical state, which has your hypothesis, and the hypothesis can be both the quantum and the classical thing. Okay, so you have both these quantum parts and these classical parts. And for different learning procedures you could think in the literature, these classical and quantum parts behave in different manners. So later we're going to have an example. Hopefully it will become a bit clearer. But hopefully the point, the main thing to keep in mind is that sort of we try to think really of the input as just some like CQ states, and the output, so in some way also just be some CQ states, and your learning algorithm is just some channel on these objects. Just going back to the classical scenario before. Yes. Pardon? Sorry, I think was there. Yeah, W. So you want W, right? So W is our hypothesis. So that's what we want. So you can think of the POVMs as sort of like doing all of these post. You do some measurements, and on top of that, you do some post processing of the measurements and so on. And this, like you can pack all of that into the POVM, right? W. Sorry. So I mean, it's just something that later we're gonna want to minimize some loss function as well. Does that make sense? No, I haven't defined the loss function yet. Yeah. So it's gonna be now. So maybe this makes it easier. So right. So what we are trying to sort of minimize is this quantity over here. Okay, so we define some loss observables, okay, which are going to depend on the hypothesis, but also on the labels, right? And it's going to act on this thing over here, right? So somehow this is sort of the output of your algorithm given the data and your hypothesis, right? And you want to make sure that this thing is as small as possible. And but you don't have access to this thing. You only have access to the empirical thing. So in fact, what we have access to is just this quantity over here, which we could then try to minimize. The left hand, this. No, sorry. But this is, I mean, this is for a given sort of. You could then try to minimize the loss, right? This is just a loss for a given W. Does that make sense? Yes. Yeah. Sorry. Yeah. The same thing that we had before. Yeah. Sort of like that. There's a W. Yeah. Maybe I can blame you again, Matthias. Yeah. Just kidding. Yeah. Right. So is the setup a bit clearer now, or is it still a bit obscure? Okay, no protests. So maybe I lost everyone, or oh yeah, okay. Sorry. Yes. So, but I mean, you're not gonna consider the test data on your. Yeah. So did I screw something up? Let me just go through it. So loss is on these guys, hypothesis on and so maybe just for everyone, like the point is that here you partial trace. So over here you sort of discarded this other half, right, and just took the partial traces, and over here you have both. So just you go back to the definition. Up. Yeah. So this is the everyone, and this is okay. More. Pardon? So over here we traced out the test from. So here we still, yeah. So that's only this bit is left. And actually, and recently there was a paper by Hayashi where he sort of criticized this. So I haven't fully understood his criticism yet. But yeah. Yes. Yeah. I also don't really understand what the it came out like 2 weeks ago. I should have said it. Anyways, but I'll comment maybe later on other things I actually extended. I think I understand the extensions at least. Anyways, so then once we have defined what we have as the expected true risk, expected minimal risk, I mean, maybe we can discuss and debate whether this is a sensible definition or not, but I think that what we can all agree on is that once we have the other one should be, then the generalization error falls out immediately. It's just a difference of the two. So, so yeah, so this is, again, quantumly speaking, what we want to bound. And the fact that we are working in this very general setup poses some technical difficulties in proving such generalization errors. And okay, so what is our theorem? So yeah, so what we have is the statement of the theorem, bless you, is similar. So we assume that we have some sort of sub-Gaussianity for our estimate, and we have then precisely a term that that is exactly the same as the Radzinsky one, but we also have some more complicated things pop up, which are due to this fact that we can have more correlations somehow popping up between the different parts of the system. So here we have the Holevo chi between the sort of this. No, and over here we have the mutual information between sort of the test data and your hypothesis, which will not be there if for instance these guys are completely uncorrelated. So we see that these additional terms, they are coming from the fact that we are working in this more general scenario where we have quantum data that can be correlated. Terms. Now, okay, I actually wanted to do let's maybe skip the proof. Sorry about that. And just I'll just briefly comment on how to prove that thing. The idea is kind of similar to the Chudzinski. We resort to variational formulas for the relative entropy, and variational formulas for the relative entropy, they then have some sort of expectation value minus log some e whatever. So and in this case, you relate this to the sub-Gaussianity of the process, the second term in the variational formulation. However, the issue is that in the quantum case, you have some, due to the non-commutativity, you have some annoyances when dealing with these moment generating functions, if you will, and the different correlations we are now assuming could be present, and because of that, we get these extra terms that pop up. So sorry for not having the time to go through this, but I think it's maybe worthwhile to dedicate the last minutes I have to just give you an example of an application we have. So that's going to be in the setup of pretty good state tomography from Aronson. But we also have some sample complexity bounds that on discrimination classification of quantum states, and also this differential privacy stuff I've mentioned before. But here I'm gonna go into more detail into the PAC learning framework. So we are assuming we're gonna have some d-dimensional quantum state, and we are just you have two outcome POVMs, okay, and we want to PAC learn that particular state. So in our case now, we're just gonna, again, it's a d-dimensional state. So our training test, our train and test Hilbert spaces are like this. And because it's a two outcome, we only have two outcome POVMs, you can think of these EIs as just 0 and 1, right? So what we're given here is just, so what we're given in total at the beginning is this quantum classical state, where again, we're taking the expectation value over like the distribution of these states and the corresponding labels for the outcomes of the POVMs, right? And row 0 is the state we care about. And again, this P is just an unknown distribution over the labels we're getting. So in this case, our hypothesis is kind of trivial in the sense that there's nothing quantum about it, right? And the only thing we want to make sure is that we capture what this thing be. So we just want to sort of approximate well the outcome of these POVMs. And in this case, we are then able to sort of use bounds on the quantum mutual information between these guys and actually show generalization bounds for this particular setup. Now, just some finalizing remarks. I think that we have sort of this framework about how you can think of our quantum learning, but again, and generalization bounds. But as I mentioned, some people have already sort of built upon it and generalized it. So I recommend looking at this recent paper of Hayashi. I should also say that the paper of Hayashi does other things, namely which are interesting for our result. So another thing he does is, because we looked at generalization errors in terms of difference of expectations, right? And you might say that, well, I don't really like expectation values. I want like statements to hold with a certain probability. So in their paper, they looked at many versions of our statements of our setup, and then they are able to replace sort of this generalization error based on differences of expectations with statements that hold with a certain with high probability. And another thing that you might be asking yourselves is like, what are like how do I control these sub-Gaussianity conditions in the quantum setting? Like, what are good examples and so on? And I mean, Hayashi, I'm not so sure how new that actually is, but or whether we it wasn't too surprising to me. He also showed that somehow that if your loss observable is bounded, then you have this for free. So for instance, if you have bounded loss observables, you always have this sort of sub-Gaussianity, which is like a quantum version of Hüfting. So just to give you one simple example, in our paper we give some others. And yeah, so I think it's nice that we were able to have this entropic generalization, entropic bounds that have a similar interpretation to the ones by Aginsky and Shu. But I think that we still lack we still lack very convincing applications. I don't know if you agree, Matthias, but sort of I think that it would be great to have a very clear example, because always everything we do is sort of recover things which were known and through other techniques in our setup, but it's not like we get anything that is truly known. I mean, it's already nice to be able to recover few things, but I would be very happy to get something generally new out of this. And with that, yeah, thanks for your attention. Mm-hmm. Mm-hmm. So, for instance, like you can see that, for instance, if the test and hypothesis data are completely uncorrelated, right, then this mutual information will be zero. So this term will immediately disappear when you do this. Yes, yes, yeah. Mm-hmm. Oh, because in principle you don't know where these states are coming from, right? I think that's what we want to be agnostic about this. That sort of be a bit going a bit beyond of sort of the setup where they're clearly separated. So this is, I think, one motivation we had in mind. Mm-hmm. Oh, and in this case, this is zero. That term is dead. Yeah, 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 yeah. Yeah, in essence, yeah, in a more generalized, I mean, in a quantum setting, yeah, yeah. Oh, oh, so you're just saying like what mm-hmm, 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 mm-hmm. So So yeah, I guess because at the end of the day, you only care about these probability distributions. I don't immediately see why you wouldn't be, because at the end of the day, what you're getting is a classical thingy anyways, right? So I don't think, do you agree? I don't think it's, I think it's, yeah. Just yeah, yeah. Well, yeah, I think that's a very good example. Precisely, if you want to do like some fidelity estimation later and so on. Yeah. In quantum. But yeah, sorry, next question. And the learners, right? Yeah. Oh, no. I think this is just a poor formulation. Sorry, it's this and here, right? So you also need, like, with respect to W in some sense. So if you go back, right? So every possible W here, right? But this the thing here, right? So this the rest is, it's not weaker because we have this, oops, this thing over here, right? Which is a function of S as well. So we are seeing S. No, I don't immediately see what. Maybe we can discuss this afterwards. Maybe not understanding what you mean. No worries. Thanks for the questions throughout the talk. Actually, were quite nice. Other questions? Well, then, yeah. Mm-hmm. Mm-hmm. So just let me be sure I understood your question. So is there any other way of getting rid of the red terms? Is that? Mm-hmm, mm-hmm. Yeah, the second term is the, yeah. Yeah, you just it's everything. I mean, I kept saying entangled, but that's not actually true, right? You just need some sort of correlation between the two. Yeah. Actually, that's also something I was thinking now, whether we should also sell it this way as saying that like classically, because we can also treat, yeah, because there's nothing intrinsically quantum about this term, right? Yeah. Okay. And sorry again for